Okay, I'm going to go through problems that we had in class today on conservation of energy. All right, so the first one, we are going down a water slide. Woo! Um, while at the county fair, Katie tries the water slide. The shape is shown in this figure. The starting point is 9 meters above the ground, so that tells me I'm going to have a height of 9 meters at the beginning. She pushes off with an initial speed of 2 meters per second. The slide is frictionless, and we want to know how fast is she going to be traveling at the bottom. So we want to know her velocity at the bottom. So we've got a isolated system here of Katie, who's sliding down the slide. The Earth is part of the system, so we can consider gravitational potential energy. Okay. And my starting point is her pushing off. Okay, so she's got an initial speed and a height at that starting off point. Okay, so start. Oops. So we're pushing off at the top of the slide to start with. And then my end point, I'm at the bottom of the slide moving. Okay. So you always want to look for clues, about what kind of energy would be included. Here we know that she's got movement at the top and the bottom because she's pushing off. They give us an initial speed. We want to know how fast she's going to be traveling at the bottom. So I think we're going to have some kinetic at the top and the bottom. We also definitely have gravitational potential at the top because we have a height. So we're going to have some initial kinetic plus some initial gravitational potential, and that's going to equal some final kinetic. And then if we write it all out, we'll add final gravitational potential, but we already know that's zero because this height here is 0 meters. Okay. Now we're going to put in our equations that we know for these. So kinetic energy is 1/2 mv squared. Gravitational potential is m times g times h. Final, and I'm going to go back and add an I here for initial velocity, and then 1/2 mv final squared, okay, for my final kinetic energy. So she is starting off with both kinetic and potential because she's moving and she's at a height. She's pushing off the slide and moving down the slide. And then at the bottom, she's got only kinetic because now we have no more height. Okay. Nothing elastic happening here, so we don't have to worry about that type of energy. We're solving for her speed at the bottom. How fast is she going to be traveling at the bottom? So now we can just go ahead and plug in numbers. We find that mass is going to cancel out, which is nice because that is not one of our givens in our problem. Okay, so we did not need it. So we have 1/2 times my initial velocity is 2 meters per second. So 1/2 times 2 squared plus 9.8 times 9 meters, that's the height of my slide, equals 1/2. And then I don't know my final velocity. That's what I'm trying to solve for. Okay. So now I'm going to do some simplifying to find my calculator. Okay. So I've got 1/2 times 4. That's going to give me 1/2 times 2 squared. It's going to give me 2 plus 9.8 times 9. I got 88.2 there. Equals, oh, I see what I did there. Equals 1/2 times V final squared. I'm going to have to get rid of this 1/2. I should have done that before I did this, but I'm just going to take it over to the other side. This is 90.2, and then when I divide both sides by 1/2, I'm going to multiply my 90.2 times 2. So I'm going to end up with 180.4 equals VF squared. Okay, so I simplified this side. So I got 2 plus 88.2, and then that equals 1/2 VF squared. I got to get rid of this 1/2, so I added these two, and then I multiply both sides basically by 2. And then my answer is going to be the square root of 180.4, which is 13.4. So she's traveling at 13.4 meters per second by the time she gets to the bottom of the slide. So that's how we use conservation of energy for that problem. Okay, let's look at the large apple. I did this one with one class, but not the other. We ran out of time. So, okay, we've got this gigantic apple, the largest apple ever grown, had a mass of 1.47 kilograms. So suppose you're holding the apple. So that's, I think, going to be our starting point where we're holding the apple, okay? And it's at a height. And then we drop it. Oh dear, we shouldn't have dropped the world's largest apple. But we're going to catch it just before it hits the ground. So it's going to be falling, and then we're going to catch it right before it hits the ground, okay? And at that moment, right before it hits the ground when we catch it, its velocity is 5.42 meters per second, okay? And that's all we know. We know the mass, and we know a final velocity, and we want to know what's the kinetic energy of the apple and from what height did we drop the apple, okay? So kinetic energy we can solve first. For the bottom, this is a situation where we're starting at the top, not moving, like we're holding the apple. So we've got our apple held at a height. So we're going to have a gravitational potential initial energy, and then that's going to equal our kinetic final. So all our energy is going to convert from gravitational potential to kinetic as the apple falls. Okay. So this kinetic we can get by using 1/2 mv squared. That's going to be 1/2 times 1.47 times 5.42 squared. And that's going to be 0.5 times 1.47 times 5.42 squared, 21.6 joules. Oops, I can't write today. That's my kinetic energy. So that answers one question. That's also equal to m times g times h. And I want to solve for h because the second thing they're asking is from what height did you drop the apple? So I can set all that equal to 21.6 joules. And I know, again, my mass is 1.47. My G is 9.8 times H equals 21.6. Let's see. I'm going to divide 21.6 by 1.47 times 9.8. 1.5. So my height is about 1.5 meters. So we use conservation of energy there. Our starting point, we had all gravitational potential energy. Our ending point, we had all kinetic energy. We set those equal to each other because this is a conserved, isolated system of the apple and the earth. And then we solved for what we needed, which was the height. So there's 2 more problems, and those will be in the next video.